In this video, we discuss finding the interval and radius of convergence of power series, and this time we're going to use the integral test. Now remember what we talked about last time. We said that if we have a power series and it's geometric, so you're multiplying by the same thing to get from term to term, all you have to do is identify that common ratio, that expression that you're multiplying by to get from term to term, set the absolute value of that to be less than 1. And you want to solve that absolute value inequality for x. That will give you the interval of convergence. Then the radius of convergence is half the length of that interval. So you just take the one endpoint, you subtract the first one, and then you divide by 2 to get half the length. That's what you do if it's geometric. Now, if it's not geometric, we have to use the ratio test, and that's really what this video is about. We're going to go through some examples of using the ratio test to find the interval and radius of convergence of a power series. I also wanted to remind you of this fact that we talked about at the end of the last video. The interval of convergence is going to come in one of these three forms. Either your power series converges at its center only, so it converges at a point, so there's not a radius really. So we say that the radius of convergence is 0, and the interval is really this degenerate interval. It's just a single point. So you've got that case. Or your radius of convergence is a finite number, and your power series converges on an interval centered at the center of your power series. So the center is right here, and then you add and subtract the radius to get the endpoints on the left and the right. Now, in that case, the interval can take on one of these four forms. The endpoints may or may not be included. So maybe both of them are excluded. Like with geometric series, it's always this first case where the endpoints aren't included. Maybe the right endpoint's included, the left one isn't. Or maybe it's the other way around. Or maybe both endpoints are included. Either way, if R is finite, it looks like this. And the last possibility is that your power series converges for all real numbers. So the graph is just the entire real line, and in that case we write R equals infinity. It's a notation thing that sort of drives me up the wall, reminds me of completed infinity. I don't like it, but I almost want to just put it in quotes because I'm saying R can't equal infinity. But yeah, that's the notation, standard notation that we use, because we're thinking of that interval as, I guess, starting at 0 and then going to infinity. Okay, so those are the only possibilities. Now, when I say that, what I mean is it's either centered here or on an interval centered at the center of the series or on the entire real line. You never get something like this. You never get a power series that converges for a little while and then it skips some values and then it converges over here. Like, that doesn't happen. This is not possible. So it either converges at a point or on an interval centered at the center or on the entire real line. So it's either this or this or this. That's it. That's all you can get. Now, to figure out which one it is, which case you're in, you've got to use the ratio test, and that's what this video is about. So let's look at this first one. We're asked to find the radius and interval of convergence of the power series. Okay, that's what we've got. Now, I always like to expand it first, because if it's a geometric series, if it's a geometric power series, it's much, much easier to do this. So I like to expand it just to make it a little bit more obvious to myself whether or not this is a geometric power series. So when n equals 1, let's see what we get. We have -1 to the 1 plus 1, so that's -1 squared, times x plus 4 to the first, all divided by 1 squared times 5 to the first. And of course, -1 squared is 1, and we have an x plus 1, or excuse me, an x plus 4 in the numerator and a 5 in the denominator. So that's what we get. And you increase the index by 1, so when n equals 2, you get your next term. So you have -1 cubed times x plus 4 to the n, so that's squared, over n squared, so 2 squared times 5 to the n, so it's 5 squared. So we end up with negative 1 cubed is a negative. Then I've got an x plus 4 squared in the numerator. And then we've got 4 times 25 is 100 in the denominator. And then when n equals 3, we get our next term. 3 plus 1 is 4. Then I have x plus 4 to the third over n squared, so that's 3 squared times 5 to the nth, so third. So I've got a negative 1 to the fourth is negative times a negative times a negative times a negative, so that's positive, plus x plus 4 to the third. And now I've got a 9 times 125. So what is that? It's 900 plus, what's 9 quarters plus 225? 1,125. It's getting late. Okay, so that's my power series. That's my expanded form of my power series. Now I ask myself, to get from here to here, what do I multiply by? Well, I can see I've had to multiply by a negative 1 and an x plus 4 in the numerator. And 5 times 20 gives me 100, so a 20 in the denominator. If I multiply this expression by a negative x plus 4, okay, that would give me the right numerator, over 20 is 100 times 20, 1,125. It's not. So this is not geometric. It's not the right thing. So this is not a geometric power series. So we have to use the ratio test. And we've done a lot of ratio test problems already, so this is very similar to what we did very recently. We just got functions of x now. You just have to remember that x is a number as you're computing this limit. So we need the absolute value of a sub n plus 1 over a sub n. And a sub n plus 1 just comes from replacing all of the n's here with n plus 1. So I've got negative 1 to the n plus 1 plus 1. That's negative 1 to the n plus 2. And that's x plus 4 to the n plus 1 now. All divided by n plus 1 squared instead of the n squared. And then I've got a 5 raised to the n plus 1. So this is a sub n plus 1. And now we're multiplying by the reciprocal of a sub n rather than dividing by the fraction. Just simplifies our work a little bit, saves us a step. Now the reciprocal of a sub n is just this, and you just flip it and multiply. So I've got an n squared and a 5 to the n in the numerator now, and the negative 1 to the n plus 1 and the x plus 4 to the nth in the denominator. Now when we take the absolute value, the negative 1 to the n plus 1, or n plus 2, and the negative 1 to the n plus 1 are gone, because those were just alternating between negative 1 and 1 anyway. And obviously the absolute value of negative 1 is 1, and the absolute value of 1 is 1. So those will be gone. So we don't really need those anymore. And we also don't need any absolute value around the expressions that involve n, or the 5s. But we do need the absolute value bars around the x expressions. I don't know how I missed it. That should be an x plus 4 to the n plus 1. Sorry about that, guys. But we do need absolute value bars around the x plus 4 expressions, because x plus 4, it could be a negative number. The x is a real number. It could be anything. I mean, x could be negative 100. Maybe that works. We don't know. So we need the absolute value bars around that. But everything else, the n's, they're going to infinity. They're positive. And then we've got the 5 to the n plus 1 and the 5 to the n there. So we're going to do what we did last time, the same thing that we did whenever we used the ratio test in the section on the ratio test. We're going to group terms that look similar together. And that's legal because of the commutative property of, or multiplication. Multiplication of real numbers is commutative. And addition of, or multiplication of real numbers is commutative, and it's associative, which means you can group things in different ways. So that's exactly what we're doing. We're grouping things in different ways, and we're changing the order, and that's totally legal. It's fine because of the properties of real numbers. So I'm going to group my x plus 4 to the n plus 1 and my x plus 4 to the n together. As long as you keep expressions in the numerator and expressions in the denominator, it's fine. Everything will stay equal. The n squared and the n plus 1 squared we can group together because they look similar. And then I've got the 5 to the n and the 5 to the n plus 1. I'm grouping those together because they look similar. Now in the numerator I had this times this times this, and that's actually in the same order. In the denominator I've got that times that times that, and then the negative 1 to the n plus 1 and the negative 1 to the n plus 2 are gone because we took the absolute value. Okay, so you group expressions like this, and then you just use exponent properties to simplify. Remember how those work. If you have x to the n times x to the m, you just add those exponents together. That also works backwards. So I can call this x to the n, or x plus 4 to the n times x plus 4 to the first, using that rule in reverse. So I have a sum up here. It's x plus 4 to this power times x plus 4 to that power. And that's convenient because it reduces, this reduces with this now. So those are gone. Now over here, there are lots of different ways you could simplify this. You could expand this out in the denominator. That's one option. I'll take that option. Now remember, you've got to write that twice in FOIL. First times first is n squared, outer times outer is n, inner times inner is the same, last times last is 1. Don't just square the n and the 1. You're going to be missing that 2n if you do that, and it would be incorrect. You've got to write it twice in FOIL if it's a binomial. Okay, and we're going to use that exponent property here again for the 5 to the n plus 1. That's 5 to the n times 5 to the first. These guys reduce. Okay, and then this guy in the middle is an infinity over infinity indeterminate form. Since we've got a rational expression, we divide the numerator and denominator by the highest power of n in the denominator. That will get rid of the infinity over infinity problem and allow us to take the limit, which is what we want. So n squared over n squared is just a 1. In the denominator, we've got a 1 plus 2 over n plus 1 over n squared. And then over here, I've got a 5 in the denominator. So that's 1/5. Okay, and I think we got rid of all the indeterminate forms now. As n goes to infinity, this goes to 0 and this goes to 0. 2 over something very large is something very small. Same thing is going on there. And so we can compute the limit. X is just a number, so when we're done, we get the absolute value of x plus 1 over 5. Now remember what the ratio test says. The ratio test tells us that this series will converge whenever the limit of this is less than 1. And the ratio test also tells us that this series will diverge whenever this limit is greater than 1. So this is L. And remember, the ratio test is inconclusive when L equals 1. So we've actually got, it's giving us 3 different conclusions here. So this tells us that the series converges. I'm just going to call it the sum of the a sub n converges when L, that's the absolute value of x plus 1 over 5, is less than 1. So we'll multiply both sides by 5. solve the inequality. Absolute value is less than 5 when the number inside the absolute value bars is between -5 and 5. And then we subtract 1 from all three parts, and we get this. So we know that this series, the original series that we started with, converges as long as x is between -6 and 4. Okay, so keep that in mind. That's for another problem. It's okay, I'm recycling. Or not recycling, I'm reusing this paper. I'm trying to use as much as possible so we don't waste any paper. Okay. So our series converges when the absolute value of L is less than 1, and it diverges when the absolute value of L is greater than 1. All right. Not absolute value of L. It diverges when L is greater than 1. And it converges when L is less than 1, and L happened to have an absolute value in it. Sorry about that. I misspoke. So it diverges when L is greater than 1. And that means it diverges when the absolute value of x plus 1 over 5 is greater than 1. So multiply both sides by 5. Now this is something you probably don't remember from your pre-algebra class. If an absolute value is greater than a number, greater than a positive number, either the number inside the absolute value bars is greater than that number, so x plus 1 is greater than 5, or that number inside the absolute value is less than -5. And if you're saying to yourself, I do not remember that at all, it's a very simple concept, just text me through Remind and I will remind you of how that works. I just don't want to do it in the video because it's not a Calculus 2 concept. But this compound, or this inequality really represents those two inequalities, and you solve both of them for x. And this is what you get. X is less than -6 or x is greater than 4. Now, that is no coincidence. So over here we said this converges when the absolute value of this, or excuse me, when this is less than 1. So that meant x was between -6 and 4. So it converges in there. Okay, with me? Well, if this is less than 1 when x is between -6 and 4, this expression will be greater than 1 when x is less than -6, which is what I just got, and when x is greater than 4. Now, L equals 1 is the inconclusive case. Remember, the ratio test is inconclusive when L equals 1. And most students don't believe me until I show them. But L is equal to 1 at the end points of that interval. L will equal 1 when x is -6 and when x is 4. If you're not sure, I just want to show you once. So it's inconclusive when, in our case, L, which is the absolute value of x plus 1 over 5, is equal to 1. That means the absolute value of x plus 1 is equal to 5, and that goes into two cases for our absolute value equations. We've got, the only way that happens is if x plus 1 equals 5, or if x plus 1 equals -5, because the absolute value of -5 is 5. You subtract 1 from both sides and you get x equals -6. You subtract 1 from both sides and you get x equals 4. What did I tell you? L is less than 1 on the interior of this interval. L is equal to 1, and that means the test is inconclusive at -6 and 4. And beyond this, we're already sure that the series diverges because the series diverges when L is greater than 1. Okay, so keep that in mind. We've just discovered that this series converges on this interval, but we're not sure about -6 and 4. So we have to do something else for those endpoints. So whenever you are using the ratio test to determine the interval of convergence, and you get a limit, and you have to set that limit to be less than 1 and solve for x like this, you always have to test the endpoint separately, because the endpoints of that interval correspond to L equaling 1. And that means the ratio test is inconclusive at those points. It's no big deal. You just plug in x equals -6 and x equals 4 into the original series, and that's going to give you a series that you can test. And I think I made a mistake somewhere. Man, do you see it? Probably 15 minutes ago you saw it. I'm so sorry. This should be an x plus 4. So we subtract 4 from all 3 parts. Whoops. Yeah, that's much better. That's -9 and that's 1. Do. I don't know why I wrote an x plus 1 there instead of an x plus 4. So the endpoints are -9 and 1, not those other endpoints that I had when I wrote down the wrong thing. Sorry about that. So my interval is -9 to 1, and now I have to test these endpoints separately. So plug in -9, plug in 1, and you'll see whether this series converges. You've got to test them using other tests from earlier in the chapter. So let's look at our series when x equals -9. The series was this, was -1 to the n plus 1, and we have an x plus 4 to the n, all divided by n squared times 5 to the n. And we're replacing we're replacing x with -9. So that gives me this. -9 plus 4 is -5. And you've got -5 to the n over 5 to the n. If you divide those, and you can, because a to the n over b to the n is a over b to the n, you're going to have a -1 raised to the n. This says n starts at 0, but I guess it should start at 1. So we can't have a 0 in the denominator. Whoops. Okay. And now if I add those exponents, I get a -1 to the 2n plus 1. And 2n plus 1 is always odd. -1 to an odd power is always -1. And we get that. Well, that's just a constant times a p series. P equals 2, which is greater than 1. So this multiple of a p series converges. Okay, so it converges at -9. Now let's see what happens when x equals the other value. And let's see, after I've made my correction, x equals 1. And you see what happens. If x equals 1, we have a 5 to the n over 5 to the n, so those reduce. And this we can see right away that it's an alternating series that converges by the alternating series test. You could check that out by identifying b sub n and taking the limit and showing that b sub n is decreasing and all of that. You could do that. Or you could just take the absolute value of the nth term and see that you've got a p-series that converges. So this is an absolutely convergent alternating series. So this one converges as well. And I'll just say this converges by the absolute convergence test. And I'll say because this is equal to this, and that's a convergent p-series. P equals 2, which is greater than 1. Okay, so it converged at this endpoint and this endpoint, so the interval of convergence is the set of all x such that x is between -9 and 1, and x might be -9 and x might be 1, so we would write it this way in interval notation. And the radius of convergence is b minus a over 2. So we have 1 minus -9 divided by 2. 10 over 2 is 5. Okay, so that's one case. Now let's look at another example. Let's say we've got the sum as n goes from 0 to infinity of x to the n over n factorial. And we want to know where this converges. Well, when n equals 0, I always expand first to see if it's a geometric series. When n equals 0, we get x to the 0 over 0 factorial. When n equals 1, we get x to the first over 1 factorial. When n equals 2, you've got x squared over 2 factorial. N equals 3, x cubed over 3 factorial. Then you've got x to the fourth over 4 factorial, and so on. Keep going. And then this simplifies to 1 plus x squared over 2 plus x cubed over 3 factorial. It's 3 times 2, which is 6. X to the fourth over 4 factorial. 3 times 2, which is 6, times 4 is 24. And you keep going. Okay, question is it geometric? To get from here to here, you multiply by x. If you multiply this one by x, do you get that? No, you have to multiply that one by x over 2. So this is not geometric. And since the series is not geometric, we want to use the ratio test to find the interval of convergence and the radius of convergence. Okay, so we compute the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And a sub n plus 1 looks just like this. You just replace all of the n's with n plus 1's. And you're dividing by a sub n. So you just flip a sub n and multiply. All of these are positive except for maybe the x's. So the x's need to stay in absolute value. But I'll group my x's together. And I'll group my factorials together. Make sure you keep expressions in the numerator and the numerator, expressions in the denominator and the denominator. That times that is equal to that. And that times that is equal to that. So we're good. Now at this point you use exponent properties and properties of factorial to simplify this. So x to the n plus 1 can be rewritten as x to the n times x to the first. And that's because of this rule. If you are multiplying x to some power by x to another power, you add the exponents. We can just do that backwards here. When I see that, I go to that, and that's nice. We do that because we want the x to the n's to reduce. Now with these two, you always want to expand the factorial that has the larger number. in it, because if this number is larger than this one, this has n factorial inside it somewhere. So n plus 1 is larger than n, so we'll do n plus 1 times the next one down is n, and then everything after that is going to give us n factorial. So the n factorials reduce, and we end up with this. The limit as n goes to infinity of the absolute value of x over n plus 1. And as n goes to infinity, if x is just a number, and it's just a number when you're taking this limit, a number divided by something really large is something really small. So that's 0, that's our limit, and that is less than 1 all the time. This is less than 1 for all values of x. All real numbers x. So that means the interval of convergence is negative infinity to infinity, and the radius of convergence is infinity. Because it does not matter what x is, 0 is always less than 1. Okay, so we've seen two cases. We have a power series that converges for all real numbers where the radius of convergence is infinite. And then we had a case like this, where it turned out to be this one. R was finite, and both endpoints happened to be included. You always have to check the endpoints if R is finite. I bet you can guess that's the last case. We're going to try the last case now. One last example. You can kind of predict where it's going, because I'm trying to give you an example of everything. That's okay if it's predictable. So you still want to see how it's done. So I've got the sum as n goes from 0 to infinity of negative 1 to the n times n factorial times x minus 6 to the n, all divided by 2 to the n. Now, first we expand it to see if it's geometric. When n equals 0, we get negative 1 to the 0 times 0 factorial times x minus 6 to the 0 over 2 to the 0. 2 to the 0 is 1. 0 factorial is 1. Anything else to the 0 is 1 as long as it's not 0. So we're going to get a 1 there. And then when n equals 1, we get negative 1 to the first times 1 factorial times x minus 6 to the first, all divided by 2 to the first. That's going to give us a negative x minus 6 over 2. And then when n equals 2, we get negative 1 squared times 2 factorial times x minus 6 squared, all divided by 2 to the second. So I've got a negative 1 squared is positive 1. 2 factorial is 2. This is 4. 2 over 4 is going to reduce to a 2 in the denominator, and we've got an x minus 6 squared, and so on. So, to get from here to here, I multiply by a negative x minus 6 over 2. If I multiply this one by a negative x minus 6 over 2, do I get the same thing? Well, the negative and the x minus 6 works, but that 2 times that 2 should give me a 4, so it's not geometric. The series is not geometric, so we'll have to use the ratio test. Okay, so we'll take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, and remember, a sub n plus 1 comes from taking all this and replacing all of the n's with n plus 1's. Then take that, flip it, and multiply, because you're dividing by a sub n is the same as multiplying by 1 over a sub n. Okay. Now, The negative 1 to the n plus 1 and the negative 1 to the n. Those are gone when you take the absolute value, because the absolute value of a positive or negative 1 is always 1. Now, the factorials can be grouped together. I'll have n plus 1 factorial over n factorial. The 2's can be grouped together. I'll have 2 to the n in the numerator, and I've got a 2 to the n plus 1 in the denominator. And the x minus 6 to the n plus 1 and the x minus 6 to the n, those should be grouped together. But you want to keep them in absolute value because x could be negative. These guys are definitely positive, so I don't need the absolute value for that. So to simplify this, I will expand the larger factorial. I'll use exponent properties for this and this. The larger factorial is the n plus 1 factorial, so we've got n plus 1 times 1 less than that. And then over here, 2 to the n plus 1 is 2 to the n times 2 to the first. Over here, you've got x minus 6 to the n plus 1, that's x minus 6 to the n times x minus 6 to the first, all over x minus 6 to the n. These guys reduce, these guys reduce, these guys reduce. And so you end up with the limit as n goes to infinity of n plus 1 times the absolute value of x minus 6 over 2. Now, x is just a number, and n is going to infinity. So most of the time, if x is just a number, this is a number times n plus 1 over 2. And as n goes to infinity, a number times n plus 1 over 2 is going to be, well, positive infinity if the number is positive, negative infinity if the number is negative. But the limit does not exist. But if this number that I'm multiplying by is 0, then this is just the limit of 0, and the limit of 0 is 0. So we're going to get 0 when absolute value of x minus 6 is 0, which means that x minus 6 is 0, which means that x is equal to 6. And 0 is less than 1 all the time, so that means the series converges when x equals 6. But if x is not equal to 6, this is a number times something that's going to infinity. So we're going to get positive or negative infinity. Actually, no, excuse me. This is a positive number if x is not equal to 6. So we have a positive number times something that's going to infinity, so we'll get infinity. So we'll say, and the limit as n goes to infinity of this when x is not equal to 6 is infinity. And of course, that's always greater than 1. So in that case, the series diverges. What does that mean? Well, what that means is the interval of convergence is a single number, it's 6, and the radius of convergence is 0. That was that last case I told you about. Converges at a single point. Now let's go back to the original series. Sorry, there are some notes down here from a different video. Let's go back to the original series and think about what's going on. Well, it doesn't look like it's anything's going on here. I mean, this looks like a regular power series. If x is not 6, I don't see a problem. Why would this converge? These numbers seem to be getting smaller. Look at this. In the numerator, you've got an n factorial. In the denominator, you have a 2 to the n. N factorial is going to grow a lot faster than 2 to the n does. Here I keep multiplying by 2 over and over again. 2 times 2 times 2 times 2. Here I get 1 times 2 times 3 times 4 times 5. I'm multiplying over and over again, just like I'm multiplying over and over again down here. But when I multiply up here, I'm multiplying by numbers that are getting larger. Here I'm just multiplying by more 2's. So the factorial is going to grow faster than the exponential. And since the factorial grows faster than the exponential, faster than the exponential, I would expect this to diverge most of the time. But when x equals 6, all those are gone and we just get 1, so it converges. So that's the ratio test. Trying to find that first page of the ratio test. I think I already put it in the recycling pile. Just remember your power series will, actually, let me get a piece of paper so I can write this down. You've got 3 possibilities. Either the series converges at C, and the radius of convergence is 0, or the power series converges in an interval around C, and the radius of convergence is some finite number. That's the open interval of convergence. So you could get this, or you could get this, or you could get this. You might get one endpoint, it might converge at one endpoint or both endpoints or neither endpoint, but you've got those 4 cases. So it converges on a finite interval, meaning an interval that's not the entire real line, or the final case is it converges for the entire real line. So you either get this or this or this. In this case, we write r equals infinity, even though it bothers me. Okay. Now, we typically find these one of 2 ways. If the series is geometric, use the geometric series test like we did in the last video. If the series is not geometric, you have to use the ratio test. And if it's this case where the limit involves the absolute value of x plus or minus a number, if it's one of these cases, you've got to check the endpoint separately. So you plug in the c minus r and the c plus r to the original series, and you test using all of those earlier tests, or those tests from earlier in the chapter.